In this video, what we're going to do is calculate how much extra energy an electron absorbs when a specific wavelength of light is shown on a metal that is above the necessary amount for the work function. So the metal that we're going to be looking at is iron, which has a work function of 4.67 electron volts. So the first step that we want to do is we want to convert electron volts into a more familiar unit, such as joules. So to do that, the conversion is 1 electron volt is equal to 1.602 times 10 to the negative 19 joules, which gives us a work function that has the value of 7.48 times 10 to the negative 19 joules. Now the wavelength of light that is going to be shown on the iron metal has a wavelength of 240 nanometers. If we convert that into meters, what we get is 2.40 times 10 to the negative 7 meters. The next step is that we want to calculate what the energy is of the photon that has a wavelength of 240 nanometers. And so to do that, we will use the equation where energy is equal to hc over lambda. H is Planck's constant, c is the speed of light, and lambda is the wavelength. And so if we plug in the necessary values, what we get is 6.626 times 10 to the negative 34 joules seconds times 3 times 10 to the 8th meters per second over 2.40 times 10 to the negative 7 meters. So if we cancel out the meters and seconds, what we will then get is 8.28 times 10 to the negative 19 joules. And that's the energy of the photons that have a wavelength of 240 nanometers. Now, to calculate what the additional energy that an electron that's being emitted has, we will use the following equation. Delta E is the change in energy, and that's going to be equal to the energy of the photon, so E 240 nanometers, minus the energy required for the work function, so even to emit the electron. If we plug in the necessary values, what we will get is that we have 8.28 times 10 to the negative 19 joules minus 7.48 times 10 to the negative 19 joules, which gives us an extra energy of 8.0 times 10 to the negative 20 joules.